What James Webb has just discovered has left scientists baffled. When you gaze at the night sky with your naked eye on a clear night, which planets can you make out? In theory, with perfect conditions and excellent eyesight, you could spot all the planets in the solar system at different times. All except one, Neptune. It's the smallest among the ice giants and is located at the most remote distance from the Sun. Its discovery was almost a miracle. Yet this world harbors extraordinary wonders. Colossal storms that appear and disappear, winds blowing at nearly supersonic speeds, icy rings, and enigmatic moons that tell a violent past. Among all the planets in our system, Neptune remains the most unknown. But what do we really know about this blue world? Follow me, we'll investigate Neptune from the moment of its discovery to the latest discoveries that confused scientists. Hey curious, a quick note. Only 13% of subscribers actually receive notifications for new videos. So to make sure you don't miss the new formats we're preparing, it's important not only to subscribe, but also to turn on the notification bell. Discovery through mathematics. Let's start at the beginning, the story of how we found Neptune. Unlike every other planet in the solar system, Neptune wasn't discovered by simply pointing a telescope at the sky. Its story is far more fascinating. It's the only planet identified through mathematical calculations. In 1846, a French astronomer and mathematician named Urbain Jean-Joseph Leverrier was studying the orbits of the 7 planets then known when he noticed something strange about Uranus's motion. Its trajectory didn't match predictions based on Newton's gravitational theory. Leverrier hypothesized that the only plausible explanation was the existence of a planet beyond Uranus's orbit, whose gravity was perturbing its motion. After complex mathematical calculations, he declared that this 8th planet must be located at a precise point in the night sky. The incredible part? After receiving this prediction, Leverrier's friend, Johann Gottfried Galle, pointed his telescope exactly in that direction and discovered Neptune in just 1 hour. The position corresponded almost perfectly to what Leverrier had predicted. A few days later, Triton, Neptune's largest moon, was also discovered. A world at the edge of the solar system. Since that moment, Neptune has remained shrouded in mystery. It orbits at the extreme edge of deep space. At certain periods of its year, it can be even farther from the Sun than Pluto. Beyond its orbit, we find only scattered icy rocks in the void. From Neptune's vantage point, the Sun appears only 1/31st the size we see from Earth, and the planet receives about 1/1000th of the sunlight that reaches our world. This faint illumination and enormous distance have made studying Neptune with ground-based telescopes extremely difficult. Neptune is the 8th and final planet of the solar system, located about 30 astronomical units from the Sun. That is, 30 times the distance from the Earth to the Sun. 4.5 billion kilometers, 30 times farther than us. To reach Neptune with current technology, a space probe would take 13 years of travel. Because of this immense orbit, Neptune takes a full 165 Earth years to complete one journey around the Sun. This means that since its discovery, we've observed only one complete Neptunian year. Studying this ice giant is truly complex. Spotting it is difficult, and traveling there with a spacecraft is equally challenging. In fact, only one mission has ever visited Neptune, and this was possible only thanks to a rare planetary alignment that occurs once every 175 years. That probe was Voyager 2. Only in 1989, when Voyager 2 finally reached the planet, could we access an enormous amount of information about this remote world. Voyager 2's journey. On January 25, 1986, Voyager 2 left Uranus, snapping a splendid farewell shot from 1 million kilometers away, beginning its journey toward the final destination, Neptune, the last objective of its grand tour of the solar system. After 3 years of travel at 54,000 kilometers per hour, Neptune finally appeared on the horizon. These are the first close-up images we ever received of the blue giant. Voyager 2 passed just 5,000 kilometers above the planet's north pole, the closest flyby of the entire mission. Suddenly, we could see the planet's true appearance, confirm the existence of planetary rings, and discover numerous previously unknown moons. Physical characteristics and atmosphere. The distance from the Sun ensures that the average temperature in Neptune's atmosphere is extremely cold, -201 degrees Celsius. The axial tilt is 28 degrees, similar to Earth's 23 degrees and Mars's 25 degrees. This results in seasons similar to Earth's, with one fundamental difference. Each season lasts 40 Earth years. At this moment, the southern hemisphere is experiencing spring. During this season, it receives more sunlight and appears brighter. This increase in brightness is quite evident, which is surprising considering that the Sun is 900 times dimmer on Neptune compared to Earth. Even though the impact of sunlight is minimal, it remains significant. The increased radiation in the southern hemisphere warms it by about 10 degrees Celsius compared to the rest of the planet. This relatively greater heat releases frozen methane into the stratosphere, causing the brightness increase, while elsewhere on the planet, methane remains frozen in the deeper layers of the troposphere. Hydrogen is the most abundant element in Neptune's atmosphere, making up 80% of its composition. But it's the high concentration of methane, 19%, that gives the planet that characteristic deep blue color, the most violent winds in the solar system. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere. Equatorial winds reach the incredible speed of 2,160 kilometers per hour, almost supersonic flow. Curiously, most winds travel in the opposite direction to the planet's rotation. These exceptional speeds represented another surprise and highlighted how dynamic and ferocious Neptune's weather systems are. Neptune hosts colossal storms. When Voyager 2 passed in 1989, it observed the Great Dark Spot, a storm as large as Earth moving through the atmosphere. This turbulent storm rotated counterclockwise, just like Jupiter's Great Red Spot, with winds reaching 2,400 kilometers per hour, the strongest ever recorded in the solar system. A NASA analyst, Ken Bollinger, commented in 1989, "Every day you see something completely new, never seen before. It's an incredible feeling. Constant changes occur on Neptune, and they happen very, very quickly." Voyager also observed the Small Dark Spot, a smaller storm south of its larger sibling. As Voyager 2 approached Neptune, this smaller storm changed shade from dark to light. The mystery of vanishing storms. Our knowledge of Neptune's weather systems is limited, but it would be even more scarce without periodic observations from the Hubble telescope. When Hubble was launched, astronomers were curious to see the fate of these storms, to understand if they were permanent features like Jupiter's Great Red Spot. But when Hubble pointed toward Neptune in 1999, these storms had completely disappeared, and since then, other storms have appeared and vanished. The latest was spotted in 2015, lasted a few years, but it too is disappearing. Although there isn't sufficient data to speculate on how these vortices form, it could be that Neptune, like Jupiter, has atmospheric bands. Even if they're not as defined or numerous as Jupiter's, the bands on Neptune would travel at different speeds, creating vortices where the bands meet. Once started, a storm can move around the planet, even between bands, but when it moves away from its energy source, it slowly begins to diminish. and that's exactly what we've observed. Interestingly, Hubble is the only program capable of monitoring these weather changes, since in most light wavelengths, they're very difficult to spot. Hubble, however, can probe Neptune and Uranus in ultraviolet, making these observations possible. Internal heat, the difference with Uranus. But why doesn't Uranus, very similar to Neptune in composition and size, also have such turbulent atmosphere? Don't get me wrong, winds on Uranus are fast too, but at only 900 kilometers per hour, they can't compete with Neptune's. Can this all be due only to interactions with the sun and seasons? There must be something else at play to explain these weather extremes. The answer might lie deep beneath Neptune's surface. I mentioned that Neptune is the farthest planet from the sun, so you'd expect it to also be the coldest. Actually, Uranus is the coldest planet in our solar system. Neptune radiates heat from within, while Uranus emits practically no excess heat. This could be because a body as large as Earth crashed into Uranus billions of years ago, depleting all its primordial heat. Astronomers now theorize that the more active weather on Neptune is due, in part, to this greater internal heat. Internal structure. What is Neptune actually made of? Its internal structure and atmosphere are thought to be very similar to Uranus's. There's a liquid mantle of water, ammonia, and methane ices surrounding the core. Where the core and mantle meet, the pressure is so intense that methane could decompose, forming diamonds under pressure. Probably not diamonds as we know them, but there could be a liquid carbon ocean with solid diamond icebergs floating, and diamonds raining through the mantle like hail. This is just a theory though, since technology has only recently begun to recreate such pressures. Around Neptune's core, the pressure is thought to be about 7 million bar, or 700 GPPa, about 7 million times the pressure of Earth's atmosphere at sea level. The Tilted Magnetosphere. The magnetospheres of the two ice giants also share similarities. Neptune's magnetic field is offset by 47 degrees relative to its rotation axis. When Voyager 2 discovered this about Uranus, the first theory was that it had to do with its unusual axial tilt. But then it found the same thing about Neptune, which has a more normal axial tilt. So, the current theory is that the magnetic field isn't generated in the core, but rather by an electrically conductive liquid mantle, or that the mantle deflects the magnetic field from the core, giving it this strange offset relative to the rotation axis. Every planet in the solar system doesn't actually have a perfectly aligned magnetic field. Even Earth's magnetic north is different from the geographic North Pole position. But only Uranus and Neptune have such a tilted magnetosphere. Neptune's auroras. Auroras also exist on Neptune, but they're different from what you'd expect. They're extremely faint because particles don't charge much from the sun, and because of the magnetosphere's direction, they're mainly type B auroras, or SAR arcs. Earth has them too, but they're not visible, and you need scientific instruments to detect their presence. They could stretch across the entire sky without you knowing it. Another difference with Neptune's SAR arcs is that they're not found only around the poles, but rather at the planet's mid-latitudes. However, although they're faint, we recently managed to capture images of them thanks to the powerful near-infrared detection capability of the James Webb Space Telescope. In March 2025, Webb released these shimmering images of Neptune's mid-latitude auroras glowing across the planet. Interestingly, at the same time, Webb was able to notice a massive temperature drop in Neptune's upper atmosphere. Its temperature had dropped by hundreds of degrees compared to Voyager's reading in 1989, almost halving over those intervening decades. What this means for the turbulent processes occurring within Neptune remains open for investigation. But since auroras are harder to detect at colder temperatures, this may help explain why Neptune's auroras remain so elusive. The ring system. Zooming out a bit from Neptune, we come to its ring system. Until 1986, scientists suspected the planet might have rings, but weren't certain. It turns out that, like all other gas giants, Neptune also has a ring system, though very faint because it's not dense and is extremely dark. With these rings against the black backdrop of space and so far from the Sun, they're very difficult to see. Intriguingly, Voyager 2 identified several partial arc structures within Neptune's ring system. These arcs raised questions about the mechanisms responsible for their formation and stability, since they consisted mainly of incomplete and dusty rings. There are 5 known rings in total, all named after people involved in Neptune's discovery and research. The innermost is the Gale ring, very faint and very wide at 2,000 kilometers. Next is the first bright ring, Leverrier, only 113 kilometers wide. Then there's the connected Lassell ring, a very faint band 4,000 kilometers across. On the edge of this ring is the Arago ring, slightly brighter than the Lassell ring and less than 100 kilometers wide. Finally, there's the outermost and most studied ring, the Adams ring. It's only 35 kilometers wide, but it's one of the brightest rings. It's particularly interesting because it's slightly inclined and features bright arcs. These arcs have been quite stable since they were discovered in 1980, but usually planetary rings are uniform. These arcs must be material clumping and clustering within the ring, but the reason for this is currently unknown. Neptune's moons. Finally, a visit to Neptune wouldn't be complete without talking about its moons. Neptune has 14 known moons, named after water deities from Greek mythology. 7 of these moons are regular moons, meaning moons that orbit along Neptune's ecliptic with very circular orbits, or orbits with very low eccentricity. After these inner, regular moons, we get to the irregular moons, the first of which is Triton. I personally think it's one of the most beautiful moons in our solar system, with amazing patterns and this burnt orange color. An irregular moon is a moon that follows an inclined, eccentric, and often retrograde orbit. This alone sets Triton apart from any other spherical moon in the solar system. It has an irregular orbit. Triton orbits clockwise around Neptune, while Neptune rotates counterclockwise. And Triton orbits at a 130-degree angle to the planet's ecliptic, though it should be noted that its orbital eccentricity is close to zero. Its orbit is almost perfectly circular. All other large moons in the solar system are regular moons, orbiting in the same direction as their parent planet's rotation. Triton, a captured dwarf planet. This strongly suggests that Triton didn't form alongside Neptune, but is actually a captured object, specifically a captured dwarf planet. No wonder then that it's by far the largest of Neptune's 14 moons, comprising 99.5% of the mass found in Neptune's orbit. But how big is that in scales we can understand? Well, it's the second largest moon in relation to its parent planet, second only to Earth and its moon. Although smaller than our moon, it orbits closer to Neptune than our moon orbits Earth, which means it appears roughly the same size in the sky. It's the 7th largest moon in the entire solar system, and most interestingly, it's larger than Pluto. Pluto is often considered the king of the Kuiper Belt, the largest object we know of that formed there, until we consider that Triton once ruled that region before Neptune captured it. So even though Triton is a moon of Neptune, it could also be said that it's the largest and most massive Kuiper Belt object. Further evidence for this was found when New Horizons passed Pluto in 2015, suggesting Triton and Pluto share a nearly identical composition, which supports the theory that they share a common origin. How Triton was captured. If Triton was a captured object, how did that happen? Objects need to lose momentum to be captured, otherwise they'd have enough momentum to escape. Although we can't know for sure, the leading theory right now is that Triton was once part of a binary system, perhaps like Pluto and Charon. When Neptune approached Triton and its moon, gravity from the encounter would have caused the binary system to break apart, with Triton's moon being slingshot away and Triton losing enough momentum to be captured in orbit around Neptune. Triton's surface. I mentioned that Triton shares some similar characteristics with Pluto. What exactly does that entail? Well, both have a predominantly nitrogen ice surface with other ices mixed in, like water and carbon dioxide. It has quite flat terrain. Its topography never varies by more than a kilometer, though Voyager 2 did see ridges and troughs, plateaus, and ice plains. What you might find unusual, though, is that it has very few craters. This implies its surface is very young and is constantly being renewed. Like Pluto, it also has some reddish patches, which are thought to be methane that has reacted to UV light from the sun, producing what is known as tholins, an organic compound that has a presumably tar-like consistency. Although organic compounds don't mean life is present there, organic compounds are the basic chemicals from which life forms. Life likely couldn't exist on Triton's surface anyway, as it's too cold and the sun too dim to support any life form we can imagine. But what's interesting is what could be found beneath Triton's crust: the subsurface ocean and cryovolcanism. Beneath Triton's surface is thought to be a rocky and metallic interior, which gives Triton a reasonably high density for a moon at 2 grams per cubic centimeter. Because of this, and also due to the large size jump from the next largest moon in the solar system, Titania, it has more mass than all moons smaller than it in the entire solar system combined. Radioactive decay from the rocky core could be sufficient to heat and power convection in a subsurface ocean of water, much like what's thought to be beneath the surfaces of Europa, Enceladus, and some other large moons in the solar system. And just like Europa and Enceladus, cryovolcanism is an active process today on Triton. Liquid water in the mantle erupts onto the surface like lava on Earth. This is the main reason why the surface is so young. It's being actively renewed by liquid water that erupts and then freezes on Triton's surface. Some very young lava plains have been identified, sparse and flat regions, but interestingly, with a wall surrounding the plain. This is called a planitia, or in other words, a solidified lava lake. We can also see calderas, which are the collapses found at the center of a cryovolcano, from where lava plains formed. It's thought that water from these eruptions also brought minerals from the underground oceans onto the surface, perhaps even being the source of the tholins and organic matter I mentioned earlier. If this is the case, and organic compounds are found in the subsurface ocean, it means there's a possibility that conditions are right for life to have formed there. Geysers and Triton's atmosphere. We also see long lines spreading across the surface, probably faults caused by tectonic activity or freeze-thaw weathering processes. If we look at some of Voyager 2's images of Triton, we can see the results of some recent eruptions. You'll notice what appear to be dark deposits on the surface in cone or funnel-like shapes up to 150 kilometers long. However, these smaller eruptions may not originate from the mantle itself. Voyager 2 spotted some plumes reaching 8 kilometers high, but these are thought to be due to a solid greenhouse effect within the moon's icy crust. Imagine Triton's surface consisting of clear ice deposited on dark deposits like tholins. The sun shines through the ice, warming the darker, more absorbent tholins beneath, which sublimate a pocket of ice beneath the surface. As the ices sublimate, pressure builds in the air pocket until the surface above the pocket gives way, causing an eruption. This eruption also carries the darker deposits with it, spreading them across the surface again. If this is the case, a very similar process has been observed at Mars's poles, with carbon dioxide ices and darker deposits under the ice layer. This process can only exist because of one thing. Triton has an atmosphere, though not as thick as scientists initially expected. Triton's atmosphere is thin, only 0.014 millibar, about the equivalent of 80 kilometers up on Earth, though, like Pluto, this density varies through seasonal changes. Since Voyager 2's observations, Triton's atmosphere has become denser as the surface has warmed, evaporating some of the nitrogen ices on the surface. However, when Voyager 2 passed, Triton's atmosphere was still dense enough to support weather conditions up to 8 kilometers above its surface. In this image, you can actually see clouds on Triton. And going back to the image of the plumes, you can see the deposits from the eruptions all end up in the same direction, due to a prevailing wind in that region of the Moon. Like Pluto, Triton's atmosphere is hazy, the cause of which is thought to be hydrocarbons in the atmosphere not yet broken down into tholins by UV light from the Sun. The constant deposition of organic compounds through cryovolcanism, ices evaporating and freezing again through seasonal variations, and a weather-rich, active atmosphere make Triton a very dynamic world, unlike most other moons in the solar system. It's more a dwarf planet than a moon, likely a sibling of the more famous Pluto in the Kuiper Belt. All these factors combined make Triton an exceptionally unusual moon. The other moons. But what about the others? The next largest moon is Proteus, which is somewhat irregular in its shape. Normally, we only see this on smaller objects like asteroids, but Proteus is actually larger at 400 kilometers across than Saturn's spherical moon, Mimas. Why it's not a sphere is explained by past collisions of objects hitting the moon, leaving these massive craters you see. The inner, regular moons orbit around the rings, some acting as shepherd moons. The outer, irregular moons are all likely captured moons. Some of the irregular moons orbit prograde, others retrograde. Neptune's outermost moons are Psamathe and Niso, and they're the farthest out satellites of any planet we know of to date. They take a massive 25 years to orbit Neptune just once. This is because Neptune has a very large Hill sphere. The Hill sphere being the sphere in which the planet's gravity overcomes the Sun's gravity. It has such a large Hill sphere because it's already so far from the Sun's gravity has less influence around Neptune than at the largest planet, Jupiter. One of the major discoveries Hubble made about Neptune was the discovery of a new moon in 2013, which has now been named Hippocamp. Now, Hubble has discovered many moons in its time, especially around Jupiter and Saturn. But what makes Hippocamp special is that it could well be a fragment from the much larger Neptune moon, Proteus. The 400-kilometer-wide moon does indeed look like it's had a tumultuous past, with giant impact craters 50 to 100 kilometers in diameter. One of these collisions likely fragmented parts of Proteus, which then fell into orbit around Neptune. Hippocamp is probably the largest fragment, being an irregular 35-kilometer-long object, and it orbits fairly close to the larger Proteus. Orbital resonance. Finally, there's one last object that shares a strange relationship with Neptune. Not quite a moon, but certainly something captured and influenced by its gravity. 2020 VN40 is a trans-Neptunian object that orbits the Sun exactly once for every 10 orbits Neptune completes. For reference, this means it has an orbital period around the Sun of 1,650 years, while Neptune orbits every 165 years. 2020 VN40's orbital plane is highly inclined, but its precise 10-to-1 ratio shows it's in something known as orbital resonance with Neptune, captured in a delicate gravitational dance with the larger planet. This discovery helps showcase Neptune's far-reaching influence on the wider solar system. Conclusion. So, there you have it. Neptune is a fascinating world that plays an important role in the gravitational tug-of-war at the extreme edges of our solar system. Along with Uranus, it's the planet we know the least about, as we've only visited it once and glimpsed it with telescopes infrequently. There's still so much for us to learn about its weather, its internal structure, and its moons. Sadly, there are no confirmed missions planned to return to this azure world, and given NASA's looming financial difficulties, none are on the horizon. On the other hand, China is considering a proposal for a Neptunian probe that could be launched as soon as 2033. If it goes ahead, who knows what discoveries will be uncovered. I hope we do see a new mission go ahead. Neptune has so much more story to tell, and although it's extremely difficult to access, sometimes the best things in life are the ones that seem just out of reach. And for us, there is no planet in our solar system harder to explore than this. The final planet, Neptune. Okay, guys. So, what do you think? Did watching this video raise any doubts or questions? Let us know in the comments. And if you want to learn more, check out the complete series we've dedicated to the solar system planets.